So hello friends, my name is Sandeep, and today's topic of discussion is axial flow fan analysis when it is rotating at certain RPM. For this analysis I am using software ansys 18.1 and 18.2 because these are the updated version of ansys, and there is several function in ansys 17 at that time, as that one was a non-updated version, so we have to produce a contour or a CD factor, coefficient of discharge factor, during analysis, but in updated version we don't have to put that. So that I'm showing you now. Then so so how to evaluate the design fan with a parameter basis. So if your fan is rotating at certain RPM, how much amount of blown air it will be giving at certain RPM. So this type of situation arises when you design a fan. And there is one most important phenomena, that is noise analysis, noise production in the fan. So in the previously I made one video on CFD fan analysis, but that one is different, because at that time the fan is stationary, is not rotating, and we are applying a velocity of air and bombarding the air on fan and calculating various factors. But here I am rotating a fan at certain RPM, and we will be checking that in the result parameter. We will be checking that how much of air will be exposed, or how much air delivered by the fan in what velocity within a defined region. So CFM extraction, this is our the result parameter. Air volume rendering and blown offs of the air, lift and drag produced during the rotation, turbulence intensity of air, pressure and velocity contours. We will be obtaining that on ANSYS software. Graph plotting between parameters for better understanding of results, and setting up of stationary animation to see the optimal result. Here I am showing you how air is flowing from backward inlet region to outlet region. At the backward region the pressure is below the gauge pressure, and after the rotation forwarded in the forward direction, the velocity and pressure is continuously increasing. So these are some static result. In the previous made video having this type of analysis, but in this video the result will be different, because for smaller axial fan, we can do static analysis and the result will be good or optimal. But when you go for bigger customized and design fan, bigger customized fan, so you can do better analysis by rotating it and calculating the CFM obtained during that. So these analysis also correct, and that form of analysis also correct, but it can vary situation to situation. You can go through both the videos, and you'll find that the result is optimally same. So this is our ANSYS module, and I have opened the design modular here. Now I'm importing one geometry file. Make sure you can save it as a step file, step format. Now the file is successfully imported here. So we have to create a boolean here. Two types of boolean. First is rotating body and second is enclosure, or a region in which we are rotating a fan and we are defining a boundary condition for that fan. So first select millimeter as your SI unit or working unit, then go for enclosure, and now in enclosure I'm selecting a box construction. So sorry, first we have to create a rotating enclosure. We are not selecting box. This is cylinder, and cushioning radius will be this radius defining the end of a fan blade and the shrouding area. So you can keep it as minimum as possible, but for desired and various reading through various research paper, I found that 2.5 is better, as it is generating lower turbulence. Lower turbulence we will be getting at the end of fan blade during rotation at high RPM. And then this will be 100 mm, and this will be 100 mm, and generate. Sorry, I made one mistake here. The cylinder alignment will be Z axis because the axial axis of this fan is Z. That's why if you select this Z axis, then the enclosure will be made in this way. So now it is time for second enclosure. For tool enclosure, now this time it is a box, 700 mm, 700 mm, 700 mm. Now this direction is minus Z axis, so in this forward region we want larger volume, so I'm giving it as 5000. So when you generate, the box type enclosure will be appear here. So this is our volume region, and let me rename the part. This one is fan, this one is rotating body, and this one is solid. Now it's time for boolean creation. We have successfully made an enclosure around our fan. So go to create, then boolean. We have to subtract the area, target body. Target body will be this, and the tool body will be this rotating body. In this case, I have to preserve that rotating body for further creation of boolean, and generate. It is our first boolean. Now it's time for second boolean. Again subtract target body. Now this time target body will be rotating body, and tool body will be fan body. And I don't have to preserve this because I don't have to create a second boolean, third boolean. So generate. Now you'll see only two entities are remaining here because the rotating body itself submerged the area of fan blade which we have rotating at a certain RPM and obtaining a result. So I'm moving to meshing process. So after closing the design modular, we have to go for meshing. Now here our fluid flow fluent will be successfully, so our geometry is successfully imported in the fluid flow fluent for meshing condition. I'm going for mesh. So here is our mesh tool. automatic method, going for automatic method, whole region, then apply. So now after going for mesh, I'm not giving a sizing because it affect our computational time. If we are going for actual design fan, in this your result will be very materiable. So you can go for curvature and select proximity and curvature, because in on that region it is generating good mesh, defined mesh. So after generating mesh, so our mesh is generated here. You'll see this is the non-structural or non-uniform mesh. By doing on this type of mesh, you'll get some distorted results. But after going, you can do this analysis in this type of mesh only, but make sure that in the analysis you should step up your iteration up to 100 or 500. But I'm creating a uniform mesh here. So I'm inserting this face meshing tool and applying to all my external region. Apply. Update a mesh here. When you update a mesh, you'll get a uniform mesh. So this meshing method, cell creation, is better for our result. Now it's time for name selection. So this is our inlet face. Inlet. This will be outlet. In the 2D analysis, we have to give the boundary conditions and defining them as a cell, but in 3D analysis we don't define walls because it is automatically generating the connecting face between the rotating fan and wall condition. So from here I will be updating my meshing for the further analysis. Now the mesh is successfully updated. Now we have to close design modular, meshing module. Now going for setup, I'm going for double precision. Every time I will be going for double precision because for double precision our iteration is solved optimally, and This is the fluid flow fluent CFD module. Here we have to apply different boundary conditions for analysis of a rotating fan. We are going for transient analysis. So go for viscous laminar and select here from K epsilon equation. K epsilon model will be realizable, and the standard wall function is not desired here. We have to define a scalable wall function. After, it's time for selecting material. Material will be air. You can adjust the value from here, ideal gas and many more. But I am keeping as it is. Cell zone condition. You'll see cell zone condition will be rotating body and solid. In this, between these two regions, solid body is boundary condition and rotating body will be imposing air on the solid body. So going for boundary condition, this will automatically generating some contact regions, as we have to go for cell condition, and we are going for rotating body. Go for edit. Now mesh motion, we have to move it, give a rotation to that. So it is automatically in line with the z-axis because our model is made in such a way that its hub origin is z, lying in a z-axis. So z will be 1, and set the speed. Here I am giving it 1000 radian per second. You can also change this unit from radian per second to meter per second. You can also change this unit into RPM. So go to unit, angular velocity, RPM, and default. So okay, so this will be our RPM. Okay, now solid body, edit, make it as it is, because it is a stationary wall. Mesh interface, 2 contact regions are formed for mesh interface. Go for methods. Simple method will be applicable. We are not going for periodic. First order appoint. Okay. These are the delta time, flow time, and per time step, iteration per time step. You have to select initialization, and I am here doing hybrid initialization because it is a time based analysis in a discrete manner. Time will be increasing in a discrete manner. Starting of iteration will be 0.03, and I'll be conducting total 30 iterations. You can go for maximum iteration up to 500 iteration, but my system configuration does not allow me to do that. So if you have a better system, you can go for higher amount of iteration, so that you will be getting exact or optimal result. So here hybrid initialization will be done. Hybrid initialization is done. Then go for calculation activity. If you are a new user, here CFD compatible is already there, but in my case it is not there because I have deleted that. So solution data export. From here select CFD port compatible, and these are the quantity which you can evaluate in this condition. I'm going for static pressure, total pressure, velocity axial velocity, and many more. You can go through all the steps: turbulent kinetic energy, and turbulence intensity, epsilon rate, turbulence viscosity. You can also get the axial and angular coordinate for the for the fan blades. This result will be better. And here you can browse where you want to save the iteration files. I'm browsing it for my desktop. You have to create one folder here. So again, go for here, desktop, and select new folder. Okay, desktop, sorry, browse again. Stop. So the frequency time step. I am ordering a program to calculate or record the result after each 2 time steps. So it is set. Now it's time for calculation running. But for that we have to set up a time first. So it is advisable to start a simulation from the very lower time step, from very lower region. That's why you can see I will be starting from 0.03, and number of time step for the you have to provide different iteration for the different result. First I am giving 50. First I am giving 40, and the maximum iteration will be 20. After calculating this time step, you can give it 100 and maximum iteration 80. And similarly, you can increase the number of steps and evaluate your result at a different parameters or different intervals. When you are evaluating your result at different interval, you will be getting a difference between these time steps. So in this condition, I will be not showing you every iteration. I will be directly showing you my results formation. So maximum iteration will be 20. Then go for calculate. So see, it will be calculating. Let's skip the calculation part. So our calculation is done. It is going for 45 iteration, but it is stopped here because I have set the time step will be 40. So let's see some result contours. So go for graphics, contours, and here you'll get all of the resulted parameters such as pressure, static pressure. Go for all the regions, save and display. So this will be pressure result, but this is not our result contours. We will obtaining those result on result section. For plotting different parameters, I have shown you in the previous nozzle analysis video how to plot this. You can refer that video for plotting different contours here. So here I am closing this fluent. After closing the fluent, you will see this solution is paused here, but it is not paused. You have to right click on that, and it will take some time because result is big. So accept interrupted solution as up to date. So it will be right click here. Now going for results, it is opening CFD post here. In the CFD post, we will get to know the better visualization of our result with the static animation. So you will see the CFD post is open up, and so our boundary region, rotating body, and including with fan. So this is the tree for our simulation. First I am locating a ISO plane here. So select it as YZ plane, and it is at mid. Apply. You will see plane is showing here. Now go for vectors. I am calculating vectors along this plane only. The location will be our rotating body, and vertex equally spaced. Number of points will be 100, and then apply. So this is the velocity we will be obtaining, and now we are going for contours. So all fluid flow domain, location inlet, pressure. So these are the pressure variation. Location will be plane 1, and okay. So you will be seeing that the pressure region here. Now compare the result with this. Now when you doing the different iteration by considering 0.5 and 0.1 iterating value, then this result will be changing, and for that you have to calculate manually the optimum average result. So this is the volume rendering of air which is blown out of the fan, and similarly you can go for streamline. These are the streamline which you will see. This is the green lines. So this entire area will be affected. In this way you can generate different result, and for better optimal results, I made a separate video for demonstration of how to use this CFD post. You can go through that.